Others, and the speaker is Attilio Castellarin. The title is Performance of Statistical Interpolation to Traditional Methods for Design Flat Prediction in Enclosed Basins in the Southeast United States. Please.
Thank you, Alberto, for the introduction. Welcome, everybody. Let me start by acknowledging my co-authors, Stacy Archfield and Julie Young from the USGS, Jon Skoyen from JRC, and Alessio Pugliese, a graduate student from my university. The study deals with the prediction of flood quantiles in engaged catchments through regional approaches, statistical regional approaches. The starting point of classical regionalization scheme is the identification of a homogeneous pooling group of sites, as we saw this morning. Here on the slide, you have a figure that you can see a figure that I've stolen from one of Ta's papers that shows the evolution in time of the concept of homogeneous region from geographically contiguous subdivision to non-contiguous homogeneous region, the output of cluster analysis, for example, to the more recent focused pooling, where sites are pooled together according to the affinity to the target site, the site where we have to produce our estimate of the design flood. As you see, the concept of a homogeneous region becomes more and more evanescent as we move from the left to the right, but still there's some degree of subjectivity in that, and the identification of the group is one of the most critical steps in any regionalization procedure. Recently, the literature showed that geostatistical interpolation techniques can be effectively used to predict hydrometric indices, low flow indices, or flood quantiles in engaged sites. In particular, the literature showed two different procedures: topological kriging or dot kriging and canonical kriging. These are the two techniques that we will focus on. Dot kriging or topological kriging, what is this? This is a geostatistical interpolation technique in the strict sense. What does it do? It performs geostatistical interpolation of the hydrometric index of interest, like a flood quantile or a low flow indices, along the stream network. How? Through basically a block kriging procedure in which the support area is the catchment area. So in the weighting scheme that is characteristic of any geostatistical approach, these are our empirical values and these are the estimate, our prediction in the engaged sites. In the weighting schemes, it takes into account the size of the catchment and the nested structure of each catchment. It's a geostatistical procedure in the strict sense because interpolation is performed in geographical coordinates. Canonical kriging, very different, even though also in this case we're using a kriging approach. In this case, the interpolation is performed through a point kriging, where not on the geographical space anymore, on a two-dimensional space, x and y space identified below, where the coordinates are catchment descriptors, are derived from catchment descriptors like mean annual precipitation, catchment area, and so on and so forth. Any catchment is a point on that size. If two points are close in the space, it means they are hydrologically similar. On the third axis, we can place the empirical values of the hydrometric index of interest, and through universal or ordinary kriging we can interpolate empirical values. Then at engaged location, an engaged location is again a point on that plane, we retrieve the index of interest, the flood quantiles, for example, from the surface. These techniques are interpolation techniques, statistical interpolation techniques. They share a common idea, that is dispensing with the delineation of homogeneous region, of homogeneous pooling group of sites, even though they refer to two different things: the geographical coordinates in one case and the physiographical space or space of characteristic in the other case. Literature presents a comparison of the two methodologies relative to the prediction of low flows, but no study is reported in the literature comparing the two methodologies for the prediction of flood quantiles. So this is the first objective of our study: compare top kriging and canonical kriging with a traditional approach for predicting flood quantiles in engaged location. Also, since I already mentioned that the two methodologies are rather different in nature, we wanted to see if blending them, coupling them, could enhance the prediction of quantiles in engaged sites. So we also tested two different blending strategies. The first one started with the application of classical top kriging in cross-validation. We obtain prediction residual in cross-validation, which we model through canonical kriging to see if this further modeling can adjust the initial prediction we got from top kriging. We call this blending strategy adjusted top kriging. We also perform an adjusted canonical kriging, in which we apply a classical canonical kriging in cross-validation, obtain prediction residuals, which we model through top kriging, trying to see if applying top kriging after canonical kriging can improve the estimates that can be obtained by canonical kriging. The study area. Study area is a set of 61 string gauges located in the southeastern US, for which several catchment descriptors are available in a recent report from USGS, together with empirical estimates, at-site estimates of flood quantiles for various return periods. We considered for 10, 50, 100, and 500. And also, the report proposes a regional framework for estimating the flood quantiles in engaged location through a generalized least square procedure. This was our benchmark methodology because it's the methodology recommended for the study area. We applied top kriging and canonical kriging. A few more words on canonical kriging. First, of course, here is a table reporting all the catchment descriptors we had for the study area. You see some morphological indices on land cover and soil properties, and some indices at catchment scale on the rainfall regime, mean annual precipitation, but also rainfall quantiles. It's a rich database, but these are the usual information you can obtain for catchments, age catchments. A couple of words on canonical kriging. The critical point here is the definition of the two-dimensional physiographic space. How did we perform this? We performed this through canonical correlation analysis, which was presented already this morning. So we got a background idea on that. In this specific case, we wanted to identify some measure of hydrological affinity between catchments, starting from two groups of variables. Our first group is the set of catchment descriptors, all the catchment descriptors that you saw before, which I termed D. And on the other side, I would like to find a pointer, but since I don't, D. On the other side, the flood quantile, the at-side empirical estimate of the flood quantiles we had for all the 61 gauged catchments. From these two set of variables, we derived through canonical correlation analysis two derived variables, termed U and V. U and V are linear combination of the original variables. That is, U is a linear combination of catchment descriptors, and V is a linear combination of the flood quantiles. But they are identified by maximizing the correlation between the two sets. We then used to identify the 2D space as X and Y, the two yellow labels you saw flashing before, the first canonical variable derived on the basis of catchment descriptors, and the second one. Which are the characteristics of these two? They are independent by definition, so they form an orthogonal space on which performing the interpolation, and they are highly correlated to the information we're interested in. That is the flat quantiles. Once defined this linear transformation, each catchment becomes a point in that space. Okay? Then we apply a kriging technique to interpolate the third dimension, and the third dimension is the flat quantile, the 10-year flood, the 50-year flood, and so on and so forth. We always use cross-validation procedure to perform this analysis for all the methodologies we tested. And the cross-validation procedure we use is the jackknife cross-validation procedure, or leave one out. Basically, for applying top kriging, canonical kriging, or generalized least square regression, we simulated engaged condition at each and every side. How? We rotated each side, so let's consider side I, for example. We supposed this side to be engaged. We dropped the hydrometric information available at the side, the flat quantile, and we estimated the flat quantiles for this very side applying the three methodology we considered. We repeated this in turn for all the n sites, where n is 61 n sites we had in the dataset, and by comparing empirical estimates with the cross-validated estimate, we get a representation of the prediction capability of each methodology when it is applied in engaged location. That is our goal. Here are some results. You can see three series for just two recurrence interval, two return periods, 100 and 500 years. The results for 10 and 50 are more or less the same. The series are the representation gauge-wise of the prediction residual with the three methodology. Our benchmark, green, generalized least square regression, top kriging, red, and canonical kriging, black. We see that more or less the three procedures perform more or less the same. There's just this particular case for canonical kriging that needs to be pointed out. This is the largest catchment in the area, and for this we obtain a large overestimation of the flat quantile. These results are summarized in terms of Nash-Sutcliffe efficient. The bar on the left of each of these sets of two bars for canonical kriging, top kriging, and generalized least square regression. Here and here. By comparing these bars, Nash and Sutcliffe efficient, we can see that top kriging overperforms the other two methodology by a large amount. In particular, canonical kriging seems to provide the lowest performance, but this is associated with this very side. So in order to dampen the effect of this misprediction, we use the log Nash-Sutcliffe efficient. That is basically Nash-Sutcliffe efficient applied to log transform flows. And the results are reported in terms of bars, the bars on the right in this case. As we can see, the performances of top kriging and canonical kriging in this case level off, and both methodologies overperform relative to the standard approach, generalized least square regression. This is evident also in these two scatter plots. What is this? It's a representation of the absolute prediction. No way. Absolute prediction error from the application of generalized least square. Here. And absolute prediction error for the application of canonical kriging, black, and top kriging, red. It points on this lower right side of the diagram. I tried, but it doesn't show up. It means that canonical kriging or top kriging are doing better or much better than GLS. And as we can see, in more than 40 out of 60 cases, these two procedures perform better. Okay, since they are so different in nature, can we blend them and improve even further the results? We try to do that with those two blending strategies I already mentioned before. But the result we obtained were not so exciting because in terms of Nash-Sutcliffe efficiency measure, we saw some slight improvement, but I consider this improvement not even worth it spending another slice to show you, because the improvement was very, very limited. And considering these two diagrams, they are more or less the same. Here we are comparing with generalized least square regression the two blended approaches, so the adjusted canonical kriging, black, and the adjusted top kriging. It didn't change a lot. Why? Well, first of all, because we started from an excellent starting point. All efficiency measures, particularly from log transform flat quantiles, were high, above 70, between 80 and 90, and we are applying this methodology in cross-validation. So excellent starting point of top kriging. But there's also something else. What is there? I try to represent using these two diagrams. What are these diagrams? They both report the distance between pairs of catchments. Each dot, gray dot here, is the distance between two catchments in terms of prediction residual and distance of physiographical space for top kriging prediction, or distance between catchment centroids for canonical kriging prediction. Okay, what do we see here? Here we see that what do I mean by distance between prediction and residual? If the two methodologies tend both, if the methodology tend for two different catchments to overpredict, then the prediction residuals should be close together, and we should be down here. If the prediction residual for two catchments are totally different, overprediction on one side and negative bias on the other side, then the dot would be up here. If applying to the top kriging result, the canonical kriging, we see that the distance in terms of prediction residual doesn't change, doesn't increase, as is the case with the distance on the physiographical space, then we have no real advantage in applying canonical kriging to top kriging residuals. And here is the same for the other blending strategy. If we see that the distance between prediction residuals is not correlated with the distance between catchment centroids, then applying top kriging will not enhance the result. And this is what we observe for this study area, that basically blending strategy number one did not enhance the result a lot because there's a lack of physiographical structure in the residual, and the other strategy is paying the fact that there's a lack of geographical structure in the residual. To come to the conclusion, we saw that top kriging and canonical kriging consistently outperformed the reference approach for the study area, with the highest performance associated with top kriging. Top kriging slightly improves the application of canonical kriging, but as I said, for this study area, the improvement is very, very marginal. And also, the comparison underlined an important distinction between the objective of regression-based versus spatial interpolation method for estimating flat quantiles, which open up a new problem on which we're working now. I try to summarize this point at the bottom. Top kriging produces the best performances because it exploits directly the cross-correlation among sites. So nested catchment are definitely cross-correlated. And we compare the output with empirical at-site flat quantiles, which may or may not be a good representation of the true unknown flat quantiles. And we're trying to compare these procedures with a reference term that is more associated with the unknown true flat quantile than the empirical ones. I've been long for, I'm sorry, I was a little long, sorry, and thank you for your patience.
Thank you, Attilio. Questions? Please, Aldo and Dimitris.
Since you're using a kriging procedure, I was curious about the biogram. I guess you're using a biogram. How did you estimate it, and what's the meaning of the range in the biogram under this framework? We
tested several options, also in cross-validation, while performing the two methodologies, by implementing the two methodologies. And for the canonical kriging, the variogram that performed the best with this case studies was the spherical variogram, whereas top reading is classically applied with the Gaussian variogram, and Jans-Koyen warmly recommended to use that, so we didn't change around the variogram applying top reading. The range in the two cases is different because in one case you measure space on this physiographical space, and in the other case it's really the distance between the centroids of the catchments. Thank you for
Dimitris, and then
you send, and I understand when you have nested basins, nested catchments, then the top ranking is of direct use and should perform good results. But when you have different basins far away, how can this method be used?
Exactly. This is what we found comparing top reading and canonical reading for the estimation of low flow, unfortunately in a totally different area in Italy. And we saw that in that case, canonical reading worked much better than top reading because, for example, headwater catchments are never nested one into the other because they are headwater catchments, and they are normally far apart, the one from the other. So for those, top reading gave was characterized by low performance. And instead, for these catchments, canonical reading provided the best results because these catchments are close in the physiographic space. We didn't find the same results for flood, and this puzzled me a little bit. It may depend on the study area we are working on. Here, invariably, top reading provided the best result.
I have also a couple of questions for canonical readings. Okay, you have in the x-axis the flat quantiles, and then you have also in the z-axis
canonical reading. X and y are different descriptors.
Yeah. You said the y-axis is flat quantiles. And then
the z-axis, the third dimension.
Okay, what's the y-axis?
The y-axis. Shall I go back to the image? Maybe I wasn't clear. I'm sorry. So I was long and unclear. That's very good.
we were saying that we are not something.
I wanted this exactly. So the third dimension is the stream flow index. So it could be a flat quantile or something else. On the x and y axis, catchment descriptors. In this case, linear combination of standardized catchment descriptors.
But again, in both axes we have catchment descriptors.
Yes, but weighted differently so that the two resulting variables are independent of each other through canonical correlation analysis. There are linear combinations in which you have different weights for different catchment descriptors that are independent. Well, it's not principal component, but it's not similar.
Descriptors.
It's very parsimonious because it's a canonical correlation analysis, like principal component analysis, are multivariate techniques to reduce the dimensionalities of your work, of your space, okay? And they develop variables, derive variables through linear combination. There are projection systems through linear combination, and these derived variables are, the first one is the one that explains the most of the original variability of your original m-dimensional space. The second one and the first one explain the most. You have to choose two among m, and so on and so forth. So by selecting the two, you already explain more normally than 80% of the initial variability.
Okay, I'm curious about the question of, okay, you first, and I think we for challenging Attilio.
I will try to be very quick. So, do you think it would improve if you use some additional information, some covariates in the greens, maybe using external greeting or using co-greeting for that? Do you think this would improve the result?
Yes, I think it would, but not on this study area, because this is exactly what we are doing by blending top reading with canonical reading. No? We apply standard top reading. It just looks at the size of the catchments, the geographical location, nothing else. not the rain, nor the perviousness of the catchment, morphology, nothing. Then we applied, we tried to model the residual with canonical kriging that looks at other things like the climate, morphology, and so on and so forth. It's like having an external tree in a sense. So the answer to your question is, I believe that there are regions where blending canonical kriging and top kriging produce an improvement in the result, or using an external tree in canonical kriging produces an improvement in the results. Unfortunately, not here.
Okay. Julie, your question?
Yeah, I was wondering why you use only two covariates X and Y from the canonical convolutional analysis.
Actually, there are already tools that develop kriging in a three-dimensional space. No, so we could have used even U1, U2, and U3, explaining even more.
That could improve.
That could have been done, but already in this case, U1 and U2 explain. Even though we started from more than 20 descriptors, you saw them, U1 and U2 explain more than 85% of the initial variability. Okay. So it was best to use a simpler model in this case, just a 2D interpolation. But you're right, you can do 3D interpolation. Okay. They're harder to represent though. I wanted to show you a nice surface, and in that case it wouldn't be possible. I'm kidding.
I think it's time for you to take a rest. Thank you very much for the talk and the discussion.
That made my trip worth it. Thank you.
Indeed, very interesting. And now I would like to invite on the floor Professor Giorgio.